So thank you. And thank you for the invitation. I think, as Francis said, this is the slightly awkward combination meeting between the workshop and a general audience talk. So the way I'm going to try and handle this is I'm going to, in some sense, tell you my talk backwards. What I mean by that is the very last thing I'm going to tell you is the thing that put me into this project. The thing I'll tell you in the middle is the thing that we realized we needed when we're doing. And then I'm going to the thing I'm going to tell you first, which I think is broadly accessible. So in particular, if there are any non-algebraic geometers in the audience, this bit is more for you as well, is the thing that we really realized we needed. So let me really start, though, right at the start with something that I'm confident everyone knows, which is the fundamental theorem of algebra, right? We know that if we have a polynomial with integer coefficients or rational or even complex coefficients, it has a root in the complex numbers. So what we're saying here is that the field C is algebraically closed. But so the question I want to start with is, what if I replace the complex numbers by a field of rational functions? So let's start with just rational functions in T. For example, you might have a polynomial like x cubed plus 3t squared plus 1 times x squared, 5, etc., etc. The point here is you should think about the T as living in the coefficients and the variable is the x. So our goal now is to solve for x in terms of T. So this is something that once you think about it, and again, this stays as your first or second year undergraduate material, the first thing, once you think about it, you see if I give you some polynomials, like x squared plus t cubed minus 1, you realize that I'm just asking you for the square root of 1 minus t cubed. And you remember your Taylor series and you expand it out. Okay, so what you can see here is that we do have roots, but we have to think about them as living in here. I'm writing Laurent series, so the field of fractions of formal power series. Second example, if I had something simple like x squared minus t, well, there you know that the answer should be plus or minus the square root of t. We just have to make that make sense. So I can think about that as living in, again, Laurent series over the square root of t. So in general, if I start with a polynomial with coefficients that are polynomials or rational functions in T, I can always find a root in the Poisson series. So the Poisson series I just take the union of all rational functions, all Laurent series in T to the 1 over n. That's going to form a field, right? If I have a Laurent series in T to the 1/3 and a Laurent series in T to the 1/17, then I just chose two numbers that I shouldn't have, then I get, if I add them together, and I can think of those as Laurent series in T to the 1 over 51, or whatever the correct arithmetic was. Okay, so these, we can add them, we can multiply them. Laurent series were already a field, so we can divide them. So in general, I'm looking for series, like formal power series, with rational exponents for the T's, with the requirement now that for any given series, the rational exponents have a common denominator. They live in a T to the 1 over n for some n. Okay, so you can see here at the bottom line, we have an example where the n is 3. My exponents are going up, but they always have a 3 as the denominator. Okay, so that's an example. And this goes back originally, Newton discovered this first, I think it was, which I think at least Wikipedia claims this is the 1676, was rediscovered by Poisson. We're starting to think about fields in this fashion in the middle of the 19th century. And if I give you F, we have an algorithm to compute these Poisson series fields. The example, but I didn't write out the full details, but just if you stare at the picture, the algorithm starts by saying, if I give you the polynomial, the first thing we're going to plot is its Newton polygon, and that is what? The 3 dots are the representatives, the valuations of the coefficients of 1, x, and x squared. So x squared has a coefficient 1, so that's why it's on the x-axis, the plot 2, 0. We go t times x, so I say x, I remember a 1, t to the 1, so that's the 0.11, and then the constant term t cubed plus t to the 5th, I remember the 3, that's the lowest power of t that shows up. I plot these, and then I just put everything that goes up from it, and you look at these two slopes. So if I look at that, the slopes here, this is a slope is -1, which tells us that my series will start t plus something. This is a slope of -2, and that tells me the other root will start as t squared plus something. And if you actually did this, right, I mean, this is just a quadratic equation, you could just treat this like your first year analysis class, plug it into the quadratic formula, get some square roots you have to do, compute the Taylor series, and you could compute the two series, and you would discover that one of them starts t plus something, and the other, well, maybe it's minus t plus something, and the other one starts t squared plus something. So the idea is that you can find out what the initial terms are from this picture, you then subtract them, plug it back into the polynomial, and keep going. So there is an algorithm in this case. And it goes back hundreds of years. And I guess probably keeps on being rediscovered in different parts of algebra and analysis as we go. Okay. For the next sort of 20 minutes, half hour, I'm going to generalize these ideas. So I first want to make the point that it wasn't obvious that we were going to just take the union of these Laurent series. And I mean, I think this is a point that we don't make even in teaching first year analysis, that it wasn't obvious that Taylor series had to work the way they did. So we could also have gone backwards. We could have, instead of working with power series and T, we could have worked with power series, Laurent series, etc. in T inverse. And if you haven't seen this before, this is a good example to actually stare at the algebra for. If you think about 1 over 1 minus t, as a formal power series, we all would automatically say this is 1 plus t squared plus t cubed, etc. But if you think about it, it's also minus t inverse, minus t to the -2, minus t to the minus cubed, etc. What do I mean by that? Well, take that last line, multiply it by 1 minus t, and you'll see formally you're getting 1, right? So that's telling you that this is 1 over 1 minus t. Okay. How do I make that make sense? Well, I have to actually have a field in which this object, the series makes sense. And the point is you could either think about your Laurent series in T or think about your Laurent series in T inverse, and which series you write down depends on your choice. Okay. And that's something that we'll see a variant of in a few slides. Maybe I should pause before I go on. That's the one, well, this is the Poisson series bit. Any questions, comments before I move on?
So you're saying you can expand that to equal 0 or infinity?
Yes.
Why not expand that to equal 1? What's special?
For me, I guess it's because I mean, honestly, oops, sorry, Zoom people as I touch the mic. In one sense, nothing. If I'm thinking about it from I think for me personally, there's hidden torus actions, so 0 and infinity actually have special meaning. Anything, other comments, questions? Next question is, what if I go away from the complex numbers? So what if I now if I don't just work over the complex numbers, if I work over another field? If your field's algebraically closed of characteristic 0, you're still happy. You can still replace the complex numbers with your field K in the Poisson series. That's still algebraically closed. Everything works the same way. Okay, Newton's proof of, well, I don't know whether Newton's proof, Poisson's proof that the Poisson series are algebraically closed, which goes with playing with that picture I showed you on the previous slide, that everything still works. Okay, so that's good. However, Chevrolet in the 50s pointed out that if we start with a field of characteristic P, then this is the Artin-Schreier polynomial, has no root in the Poisson series. So I can't I can't solve things in the same way if my field has characteristic P. Okay. And then a little later, Abianca pointed out that actually one way to see why this is wrong, and I hope I have got my exponents correct on this one because I kept on having to fix it. One way to see this is if I expand my field a bit, if I don't just look at rational function, the Laurent series in t to the 1 over n, if I allow myself the denominators in powers of p to get larger, arbitrarily large, then we can give a series type solution for these roots. So here we have, if you look, you're just going to take the sum of t to the minus 1 over p to the I. Okay, and you can check. I mean, this one you might even be able to do in real time. You can check if I raise that to a pth power, you're just using, it's a Frobenius thing, so each exponent just gets raised to the pth power by itself. And you can check that you're just getting yourself back again with a t inverse off by 1. Okay, so this is a root. So as long as we have a field where this object makes sense, and it turns out the other roots are just going to be, well, if we were working over, say, the algebraic closure of FP, the other roots are just 0, 1, 2 up to p minus 1 plus this. As long as we have a field where this series makes sense, these are the roots, and then that also justifies to you that there isn't a Poisson series root because we have a field that contains the Poisson series and p roots that are not there. Okay. So the general case is there is such a field, and the series we're allowed we're going to allow the exponents have the form m over n p to the I, so that where the n is fixed for a given series, that's like the Laurent series in t to the 1 over n, but the powers of p can get larger and larger. So we're allowed larger and larger powers of p there. And then there's this technical assumption that if you look at all the sets of p's, now that we're allowing denominators to get larger and larger, you might get accumulation points. So we have to put a technical assumption that the set of exponents that show up are now well ordered. Okay. The issue is otherwise what might happen is multiplication might not be well defined. Whenever you do these sort of generalized power series, you have to worry that when I multiply two series, if I multiply two power series, we know that multiplication is well defined because there's only actually a finite number of terms of this times this adding up to this exponent. But once things are no longer discrete, you have to worry. And it turns out well ordering is a condition that makes it work. Well ordering in the first year analysis sense, every set has these are subsets of the real numbers. We want every subset to have as ordered. Yeah. The exponents are subsets of the real numbers, and we want that to be a well-ordered subset of the real numbers. Yeah. Okay, so this is on the bottom line. We have the example. I think I have n is 3 again, and my prime is 2. So you can see that we're getting every denominator is 3 times the power of 2. And so the claim is that this forms a field, and furthermore, it forms an algebraic closed field. And we could, if we wanted, do the other trick, go in T inverse, and then instead of being well ordered, well ordering meaning having a minimum element, we would then have to say it's well ordered. Well, everything has a maximum element in the opposite way. So we again have two choices of the field to construct, but in this way we do get an algebraically closed field containing the field of rational functions. Okay, so that's one variable. I think that's question you might ask now is what about more variables? variables. I mean, Poisson series go back to Newton, that's hundreds of years. This characteristic P stuff is already roughly 70 years old. But on the other hand, what if I wanted, say, the algebraic closure of the field of rational functions in two variables? So now I'm thinking I've got my multivariate polynomial, but I want to think about it as really a polynomial in one variable, and all of the other variables you see live in the coefficients. So this is much more recent. So this covered, I mean, at least the version I'm going to tell you now, it comes mostly from papers of MacDonald in 95, and Rocca-Allardi is about 10 years ago, and Saavedra is only, I think this was his PhD thesis about 5 years ago. So this is one of these nice things that I didn't personally know I cared about this topic 2 years ago, but once I realized I cared about it, it turned out people had proved the theorems I needed in the last 5 years, which is always very nice for a project. Okay, what do we do? The idea is we're going to still think about multivariate, or you're going to generalize these power series. So we might, maybe I'll put the example up. So we'll have things like 1 plus T1 plus T2 plus T1 to the third, T times T2 to the half, and so on. But in the same way that in one variable, you have to restrict yourself to being Laurent, meaning the exponents have to be well ordered, they have to stop at some point. You make one choice that they either go upwards or they go downwards for your whole field. What we're going to do here is we're going to choose a direction. That's the W, which is that's the little arrow. And we're going to take cones, rational cones that live on one side of that hyperplane. And that's where the exponents of my series can live. So what you should think of is if you want to write a series, you can just plot the exponents as points. Instead of an R, they're now an R2. And we're going to plot those, and they should live inside a cone, a rational cone that is on the correct side with respect to this vector W. The W, this little Li, this is a technical thing, meaning the coordinates of W should be linearly independent over the rationals for this to work. There's a certain, you get into these sort of technical details about actually making the series, the set of series of this form a field, and one of them comes from this. And again, there's a well ordering condition. If I have a vector W with linearly independent entries over the rationals, that will totally order all the possible rational exponents inside my cone. And I'm asking that the set of exponents that show up be well ordered with respect to that total ordering. And again, I'm going to ask that the exponents, the denominators, all have the form n times p to the I. Okay, so you think to yourself, it's like you're trying to look at just Laurent series, multivariate Laurent series in t to the 1 over n's, t1 to the 1 over n, t2 to the 1 over n, but we're also allowing ourselves to have growing powers of p. Okay, so an example would be if C, just two variables, my cone C is just the positive ortho, so choose your favorite two positive irrational numbers, 1 and pi as my W. And then if I take a series like the rule is now my exponents have to live in the positive orthant. This is the case, P is 2 and N is 3. So again, my exponents, the denominators are all 3 times the power of 2 as we're going. Okay. And the claim is that if you do this, you get a field. If I look at all such series, I fix W. So for each choice of W, I get a field, and this field is algebraically closed. So that says if you have a polynomial in X and T1 up to Tn, and you can always find a root X equals a series of this form. And this choice of W, this is the same as a one variable of me choosing T or T inverse. Okay, because in one variable, there's only two directions, plus or minus. Whereas as we go to more variables, you get to choose many more choices. Okay, so maybe I should pause questions or. Okay. So that's okay. So that's the first part. This is the idea, and I should say, right. The last slide was a reminder for me to say a few sentences. I should have said earlier that you've seen, and actually maybe even if I go back to one variable, these generalized Poisson series, you could, if you wanted, generalize them further. Okay, we could allow arbitrary real exponents as long as the set of exponents that shows up are well ordered. This is hard series. Mirror symmetry people in the audience might be familiar with the Novikov ring that will come up. These are all sort of, there's many different examples that come up. I think this is again one of these sort of somehow elementary topics that keeps on being rediscovered by multiple different people from different directions. Okay, and for multivariable ones, I want to emphasize what I'm giving you here are algebraically closed fields that contain the rational fields of rational numbers, but they are not the algebraic closure. There is surprisingly little, this is a surprisingly open field of subject for something that's so elementary that you can tell, you can tell students in their first algebra class. I mean, in our first, whenever you teach people their first algebra class, they can understand the concept of the algebraic closure of the field of rational functions, but we don't actually know what the algebraic closure is. There's some work about, there's two places where there is partial results. It tends to be about what the supports can actually look like, so what sets of exponents could show up. There's some bits of work, and then there's some bits of work, mostly if we're starting with algebraic closures of finite fields, about what patterns of coefficients could show up. But there's still, I mean, I would say it's still very open for such an elementary question. Like this one. Well, I wanted to just say rational functions. So I mean, you could also ask about the Laurent series. Yeah, sure. So it is true that Poisson series, if we start with Poisson series, then they are the algebraic closure of the Laurent series. But if I start just with the rational functions, and I mean, this is, at least from my, as you will see in a moment, my motivation originally comes from saying, we've got something actually algebraic, every variable, but let's think about some of these variables as rational functions. And there, we don't know the algebraic closure in that sense. Yeah, so I meant it as written in that sense, as in rational functions, not Laurent series. I'm only restricting the denominators. Well, and there's this well-ordering condition too. So the well-ordering condition is also a restriction. Yes. No, it does contain the formal power series, yes. Yeah, no, but the question, right, so it contains formal power series, I completely agree with that, but the question I'm at least personally interested in is, what can we say about the algebraic closure just of the rational functions? So the small, you expect that to possibly be smaller, but it turns out to be, at least at the moment, widely open.
Is this just a characteristic P, or is the same?
So this also works over the complex numbers. You just set P to be 1 in this. Yeah. So it's this is the characteristic P version. If you're in characteristic 0, treat it like a Poisson series. So
but this issue about not knowing the algebraic closure of rational.
We still don't know that as well. Yeah. No, this is something I had no idea about 2 years ago. I guess I naively assumed that someone did understand, and the literature seems to be not very. A mixture. I mean, it's a mixture of this is a hard problem, and maybe it's been a hard problem, so people have been put off thinking about it. I think there's not a deep literature. Okay, so let me tell you now the second part of the talk about my motive. Why did I start to come thinking about this? Okay, and this is motivated more by some geometry. I wanted to think about, my day job is as a tropical geometer, so I was coming from the second part of the sentence, but toric and tropical Bertini theorems. So this is a cartoon version of the rest of the talk. On the left, we see a picture of the classical Bertini theorem. We've got a variety. We want to slice it with a hyperplane. The middle picture, as I'll tell you, is a toric version of this. Instead of slicing with a hyperplane, we might slice with a subtorus. Okay? And then the picture on the right, for people who know some tropical geometry, we have a tropical variety, and I want to slice it with a hyperplane. And so my original motivation, and I'll try and say a few words about that at the end, was to get to the last picture. But it turns out we were led to think about the picture in the middle along the way. So let me remind you first, particularly for any non-algebraic geometers, so classical Bertini theorem, I want to think about it just for irreducibility. I have an irreducible variety of dimension, at least 2, projective variety. The Bertini theorem says if I slice it with a hyperplane, unless you're unlucky, the hyperplane section is going to still be irreducible. Okay, so, and I'm going to state it the way I'm going to generalize it to say the set of hyperplanes with H intersect X irreducible is dense in the dual projective space. You could, of course, ask for different variants of this. Many times when people apply this, you might want smoothness instead of irreducibility. I'm going to stick for this talk to irreducibility because that's the thing that makes sense with the last generalization. But the thing I'm just sort of stating in some sense the obvious, though I guess for early graduate students in the audience, I personally found this wasn't obvious. There was this phase before when it became obvious is that people would just apply Bertini's theorem without even stating it clearly because it was just regarded as so obvious. We're just going to take my variety, slice it until it's a curve, and whatever. So it's often key for induction proofs, and that's what we wanted out of it in the generalizations I'll tell you about. So the point here is I want 2 generalizations. These were the 2 generalizations in the cartoon. The first is I want to replace the hyperplane by a subtorus. So we'll change, my variety will be a subvariety of an algebraic torus, and I'll slice with a subtorus instead of a hyperplane. And the other option is I'll change X to the tropical variety. So I'll say a few words about that right at the end. Okay, so I realized I didn't, Cyril, what time am I meant to be finishing? Okay. Okay, so let's start with the toric Bertini theorem. Okay, so I want to start with a subvariety of a torus. And instead of the usual Bertini theorem says slice with a hyperplane, instead of slicing with a hyperplane, I want to slice with subtorus. So I'm going to take a subtorus T prime of T and intersect it. And there's a problem though, is that we can't expect most T prime to work. Okay? In Bertini's theorem, we say, well, most hyperplanes sections remain irreducible. This isn't going to happen with if I take subtori. Here's an example. Here's the warm-up example first. If I start with X being X squared minus YZ squared in 3 space, so it's just a hypersurface in a 3-dimensional torus, it's even actually defining a 2-dimensional subtorus. And if I look at the subtorus, T prime is T1, T2 squared, T2. If I intersect X with T prime, then what am I doing? I'm just substituting in x1 is t1, x2 is t2 squared, x3 is t2. Okay, so you just get t1, the variety of t1 squared minus t2 to the fourth, which we can all see is a difference of two squares. It's going to decompose as this union of two curves. Okay, that's one example. The problem, though, is that this is kind of what this is easy to find. So here, I mean, a three-dimensional, some varieties of a three-dimensional torus, if I can think of these as discrete data, and here I've got my subtorus T prime ABC, who is T1 to the A, T2 to the 2B, T2 to the C. So the first example was just the case A, B, C, all being 1. And if I now do the same trick, I do the intersection. So that means substituting x1 is T1 to the A, x2 is T2 to the 2B, x3 is T2 to the C. Then again, I get something, you can just see that it's reducible. Okay, so the problem here is we've got this whole Z3 worth of bad subtori. It's not the case, and this is just the one example for this thing. It's not the case that sort of most tori work well. Okay, so that at first seems like a serious problem. However, but maybe I should pause questions, comments before I. Okay, so at first this seems like a serious problem if you try to generalize a Bertini theorem. Okay, we'd like to, you want a version that says most subtori work. Luckily, this is something that had already been solved. And again, this is, when I said earlier, it turns out, I realized I cared about this problem just to find out that someone had solved it a few years before. So this is a work of Fuchs, Mantova, and Zannier, appeared in JAMS in 2017. And this is a piece of I mean, this was for them. This was a corollary of some seemingly unrelated work, which maybe I'll say a few sentences about later. But here's their approach. What they're going to say is, let's not look at all subtori. Let's only look at subtori that show up in the following fashion. If I take a dominant map of X down to so if X is d-dimensional, take a dominant finite map down to a d-dimensional torus, and then I'll pull back subtori from that. Okay, so those are the only sorts of subtori I'm going to think about. I mean, that's not a serious restriction. But here's the thing. If you do that, sometimes you're going to run into trouble. Okay, when are you going to run into trouble? You're going to run into trouble if there's an isogeny. So this is a finite group homomorphism, surjective group homomorphism with finite kernels. So we're thinking something like T1, T2 goes to T1 cubed, T2 to the fifth. If you have an isogeny for which the pullback ends up being reducible. Okay, because if you do that, no matter what torus you choose down, if I choose a subtorus down here now, when I pull it back, you expect to get two pieces. Okay, and that's exactly what was happening on the examples in the previous slide. Okay, so the examples on the previous slide, I had x squared minus yz squared, and the problem was precisely that we did have this isogeny mu z goes to, so yz goes to y squared z on my last two coordinates, for which if I pull back any subtorus containing those, we are going to get something reducible. Okay, so that was the problem. So what we're saying is, we say that if we have a map of X, a dominant finite map of X onto a torus, it satisfies the pullback property, so it satisfies property PB if, when I do the pullback, the pullback stays reducible. And this is something that isn't going to be true for all examples, as we just saw on the previous slide, but you can kind of get, if you do this enough, if have an isogeny, I pull back, if I pass to one irreducible component and keep going, eventually you'll run out of things. Eventually this will satisfy PB. So it's both an important condition and a not very serious condition. Okay? So you should think about it, I mean, this is not an exact analogy, but you should think about it a little bit like asking that varieties be reduced. It's the same sort of flavor of clearly important, but also reasonable. For my X, I don't think that's very related. Yeah, I would have to think, but I don't think it's very related. Okay, so why is this a good, well, I mean, the justification for the condition is this theorem, right? So what do Fuchs, Mantova, and Zannier say? They say if we have a dominant finite map of X onto a torus that satisfies this PB condition, then there are only a finite number of bad subtori downstairs. As long as you avoid those, the preimage will intersect X in something irreducible. And you don't just take the torus, you can take any coset of the torus. Okay, taking a coset of the torus is like taking an affine hyperplane instead of demanding that your hyperplane passes through the origin. Okay, so the idea is, in this case, is as long as you satisfy PB, we do have a Bertini theorem. Okay, it is the case that there's only a finite number of bad choices and for every other torus, and you can take cosets, the preimage will be irreducible. Okay, so that gives us a version of a Bertini theorem in this case. Okay. There is an issue, though, from my perspective, and that's I've been leading you to think about the fact that I want to think about not just think about the complex numbers, think about other fields. And their paper assumes that is written over the complex numbers, and the proof really does need characteristic zero. There's some resolution of singularities and also some Galois theory that's requiring. That requires characteristic zero, and this is somehow a deep requirement. It's not the case that someone proves resolution in characteristic P tomorrow, and suddenly their paper is true in characteristic P. Their Toric Bertini theorem for them was actually a corollary of some proofs, some somehow elementary, almost computer sciencey facts about the number of terms of polynomial solutions to polynomial equations, which they proved. There was some very old conjecture that they proved in characteristic zero, and it's just false in characteristic P. So somehow the techniques of this paper are really characteristic. They're really characteristic zero statements. However, for what we wanted, at least for the motivation I'll tell you at the end in tropical geometry, this seemed bizarre. Okay. There's very few things that really deeply depend on the characteristic in tropical geometry, and it wasn't clear that these applications should be one of them. So we wanted a proof that didn't have a characteristic assumption. Okay, so let me tell you about that. So, and this is who's the we? The we this is a big group of Francesca Gandini, Milena Herring, Fatemeh Mohammadi, Jenna Rajchgot, Ashley Wheeler, and Josephine Yu. So what we say is that there is a Toric Bertini theorem in arbitrary characteristic. And let me be a bit more precise. I'm restating it because it's a slightly different statement. So you choose your favorite algebraically closed field, but you get to choose it's your choice what the characteristic is. And again, we're going to take a dominant finite map of X onto a torus. And then what I'm claiming is that the set of T prime downstairs that I can pull back and get something irreducible, that is dense in a Grassmannian. What do I mean by dense in a Grassmannian? Perhaps it's easiest to see this with an example. Okay. if I have y, so here's just one, this is one concrete example for which I know, for this example, I know a more concrete statement, but I don't have, our general proof, we only have density. I'm not able to make this precise statements in characteristic P in general. So if anyone does see any easy ways to see this, statements like this, I'd be interested in talking. So we think about this hypersurface, y cubed plus 1 plus t1 plus t2 plus t3. I want to think of it in a 4-dimensional torus over f2 bar, and pi is just the projection onto the t coordinates. So I'm claiming that for t prime being t to just the 1-dimensional torus, t prime is t to the a, t to the b, t to the c, that the pre-image is irreducible unless a plus b equals c. Okay. So what do I mean by the density? This tori, 1-dimensional subtori, I'm going to write them as t to the a, t to the b, t to the c. I can think about that as the point a, b, c in projective space. Okay, and so I want to think about, these will give me points in projective space over the rationals. And what I'm saying is your choice of these, this is dense, in this case in a dual projective space, if we wanted bigger dimensional subtori in some Grassmannian. Okay, so the claim, and this, so it's not quite the same as the FMZ had paper. They said finitely many bad subtori. We're saying the good ones are dense. So it's slightly weaker in that sense, but on the other hand, well, it was good enough for our applications. And if you think it fits with the way we think about Bertini's theorem. We think about it as, well, that hyperplane doesn't work, just wiggle it a little bit and you'll get a hyperplane that does work. And so that's the flavor of the Toric Bertini theorem. Okay, so I think questions or comments before I tell you a little bit about what is the connection of this to the first part of my talk is the next thing that's coming. Yes. Yes, that is true. Oh, but yes. Okay. Yeah. Any other questions, corrections, comments? Okay. So to give you a bit of the idea of the proof, and the reason is that this is going to explain what this has to do with the first part of my talk. Why was I led to care about the algebraic closure of fields of rational functions? So it turns out that there's a special case of this question, which turns out to be basically the entire problem. It turns out it's enough to understand this in the case that X is a hypersurface and you only care about 1-dimensional subtori. Okay? If you understand that case, the other, reducing to that case is fairly easy. Okay? So I'm going to think about X is just defined by one polynomial F in X, so it's got in T1, T2, and Y, so T1 up to TD and Y, and I'm projecting it onto the T coordinates, and the question is which 1-dimensional subtori in the T coordinates can I pull back and get something irreducible? What is that asking? Well, if I think about my polynomial, let's assume it's monic in Y, I can just factor it, right? So I can just factor F as a product of Y minus alpha I, where the alpha I live in the algebraic closure of the field of rational functions, right? And this is why, to come back to Miles's question, this is why I wanted the algebraic closure of the field of rational functions, not the Laurent series at this point. If you think about what does it mean to take a 1-dimensional subtorus, a 1-dimensional subtorus will look like x to the n1 up to x to the nd. I'm just choosing integers n1 up to nd. To do the pre-image, to intersect with this subtorus, what am I doing? I'm just substituting in t1 is x to the n1, t2 is x to the n2, up to td is x to the nd. Okay, so, and that gives me my polynomial g. So g in xy just comes from f by substitution. Okay? So the question we're asking ourselves is, I hand you F and I ask you, is it the case that most vectors n1 up to nd have the property that G will now be an irreducible polynomial? So you can see that F has a finite number of terms. When you substitute in, G has this finite number of terms, but you have to worry that maybe it can factor. And actually, this is the question about how many terms factors can have was actually the main punchline of the FMZ paper. And there are results in this world that are true in where there are things that are bounded in characteristic 0 and unbounded in characteristic P. So there's a bunch of subtleties even at this sort of level of elementary nature. Okay. Well, the question I'm asking is G irreducible? Well, let's think about just factoring G. G has factors y minus beta I, where the beta I live in the algebraic closure of K adjoint X. So one thing that could go wrong is if one of those beta I is an actual polynomial. Okay, it's not some complicated Poisson series, but it's an actual polynomial, then suddenly G is reducible. Okay, or some product of those, the product of the first three factors could have polynomial coefficients. Okay, so that's saying that some symmetric polynomials in the beta I's are suddenly polynomials. So we have we somehow care that these beta I's and their symmetric polynomials are not suddenly becoming polynomials just at X, because that would mean that G factored. Okay. In order to understand that, our hope was that you could just get beta from alpha. Okay. I told you in the first half of the talk that we can definitely, well, we know, or we knew already, we've got this generalized Poisson series for the betas, right? The betas are some series in the X's. The alphas are some series in the T's, maybe complicated exponents and whatever, but you'd like to just be able to do a substitution. Ti is X to the Ni into these series and get beta from alpha. There's a problem though, and that problem is, given what I've told you so far, this might not be well defined. Okay, what I do, you can think about the substitution as I had my cone and I'm just slicing it. Okay, the substitution is it's just some projection map geometrically. And the danger is that you might be adding together you might be adding together an infinite number of terms when you do the substitution. Okay, and this is possible. This won't happen in characteristic 0 because of the Poisson series, the exponents are discrete, but it might happen in characteristic P because I let the exponents not be discrete anymore, right? I let you have bigger and bigger powers of P in the denominator, and that might get you an infinite number of exponents lying in, having the same substitution. And so that's the problem. So this is the proof we wanted to make, but we realized that it didn't obviously work. Okay? And so that led us to sort of down this rabbit hole of thinking about what do we know about algebraic closures, and in particular, do we know more than what I told you in the previous two slides? So when I told you that we had these codes and well-ordering properties, I mean, that was the status quo 5 years ago. And so our contribution was and I won't go into the details because it gets a bit technical, but to really say, if you're only caring about the algebraic closure of the rational functions, if you don't want everything in this big field, then we won't run into problems. So then in that case, this method of taking a root alpha and substituting Ti equals X to the Ni, that will work. You won't be adding together an infinite number of terms. There is a well-defined map, from the appropriate subrings. So in some sense, what we did was we constructed a smaller algebraically closed field containing the field of rational functions contained inside these bigger ones. I am 99% sure that this is not an algebraic closure, that that you can shrink it further. But it convinced me that this is a sort of a subtle and difficult problem. And so our result was, we thought about what exponents can show up. So the structure of exponents that can show up in an algebraic, if I just take a code and I throw rational exponents there, which ones are possible? One also has to worry in principle about what the coefficients can be, and that we didn't go there. Okay, so that's the Toric-Bertini theorem. So maybe just to come back, just put the statement up again. The point was, if we have a subvariety of a torus, as long as you're careful enough, and careful enough means paying attention to this PB property, then you can intersect with most subtori, and you do get something irreducible. Okay, and our proof involved, really paying attention to. It turned out to to be something that you could really, in some sense, tell an undergraduate algebra class. We're thinking about roots of polynomials and these sort of substitutions. Okay. Oops, what have I done? I have done stuff. There we go. Oops, there we go. Okay, there we go. Okay. So why did I care about this? Let me finish by telling you how we actually came to thinking about these questions in the first place. And this is, we wanted not a Toric-Bertini theorem, but a tropical Bertini theorem. So there are many different approaches to tropical geometry. If you haven't seen it before, the one punchline is to say it's a combinatorial shadow of algebraic geometry. We're going to study varieties by looking at piecewise linear objects, like the picture on the slide, and try and deduce some geometric properties from these things. So I'm going to start with a subvariety of a torus and working over a valued field. So as long as if my field is algebraically closed and non-trivially valued, then the tropicalization of X is just going to be, I'll apply the valuation to each coordinate. I'm assuming I've chosen coordinates, and so I have a point in my variety has coordinates x1 up to xn. I apply my valuation back. If it was, for example, the Poisson series we had earlier, that would just be remembering the lowest exponent that showed up. And I get a bunch of points in R to the n, and I take the closure of all of those points in the usual Euclidean topology on R to the n. The miracle, what makes tropical geometry actually work as a field, is that this is not an arbitrary subset of R to the n. There's a lot of structure. So the theorem, which, well, the first part of this predates tropical geometry by about 20 years. So Berry and Groves were geometric group theorists who were interested in this question for well, related but also unrelated reasons. And then there's more work on this by, so BJSST is what Bogart, Jensen, Schweier, Stempels, Thomas, and then Cartwright and Payne. Say, if I start with an irreducible variety, then the tropical variety is the support of a connected polyhedral complex that has the same dimension as the dimension of X. So polyhedral complex means a union of polyhedra. Here you can see we have rays and line segments. Support means I only care about the points. I don't care about how I'm writing it as a union of polyhedra. So you'd be okay to sort of subdivide one of these line segments into two line segments. But so the points, I guess the key points here are it's connected and has the same dimension. And then there's actually a bunch of other extra combinatorial structure that I'm putting under the rug. Okay, so Josephine, you and I were interested in this connectedness result because we suspected that there would be more than just connected. This is something that you see, for example, in polytopes. If I have the edge graph of a polytope, that graph is not just connected, but it's deconnected in the sense of graph theory if your polytope is deconnected. And our intuition was that something like this should be true in the tropical world. And it turns out it is, but in order to prove that, we needed a tropical Bertini theorem. So we needed to be able to drop dimensions, slice down to lower dimensions, because to prove this connectedness theorem, the main point is actually that tropical curves are connected, and then you reduce to that case. Okay, and so this is our tropical Bertini theorem. So this starts with work of mine with Josephine and characteristic 0. So this was our first paper where we realized, this is where we discovered the work of Fuchs, Mantova, and Zannier, who would say that they had their characteristic 0 toric Bertini theorem, so we could use that. And then we joined with the rest of the group to prove the characteristic P Bertini theorem and actually get this thing in general. And so, and what does it say? It says if I have something, a picture, so a set sigma, there is the tropicalization of an irreducible variety of dimension at least 2. Then we claim the set of rational hyperplanes for which, if you intersect sigma with H, you get the tropicalization of an irreducible thing. That is again dense. So it's the same sort of flavor as the toric Bertini theorem. We're getting that the set of hyperplanes is dense in my projective space. And this answered a question of, so Cartwright and Payne, when they proved connectedness for tropical varieties, they needed to use classical Bertini theorem. So they had to worry about intersecting sigma with the tropicalization of hyperplanes. And they asked, well, could we just use your usual hyperplanes instead of tropicalizations of hyperplanes? So this is I'm saying that this is the case. And it's a consequence of the toric Bertini theorem because hyperplanes are tropicalizations of subtori. Okay, so the way you prove such a thing is you have to sort of go up and choose a subtorus where the intersection is irreducible, and then when you tropicalize that, you will be intersecting with a hyperplane. There are some details. You notice I had these, this PB asterisk in the toric version. We don't need that in the tropical version, so there's some work to get rid of that. But this lets us have a Bertini theorem also in tropical geometry. So I think I will stop there. So hopefully I've told you some surprising open questions and two generalizations of a very useful theorem from algebraic geometry. So, thank you. We don't know. The problem is somehow in characteristic 0, there's actually, so yeah, let me just come back to it comes back to this statement here. When you have this field, there was a choice of W. In characteristic 0, there's actually a finite fan for which the same W work. If I give you a polynomial, then there's actually only finitely many different possibilities for the roots. In characteristic P, we couldn't prove that fact yet. I kind of suspect it might be true. So what do I mean by that? I mean, if you get if I tell you that the roots are all supported in this cone, then that's W positive for a lot of different Ws, and your polynomial only has finitely many coefficients. So there is some sort of thing, but we couldn't do that. So we were somehow getting an infinite. All we can prove at the moment in characteristic P is some infinite chamber decomposition, which somehow stops us from having that generalization.
using much stronger assumptions.
I mean, the smoothness is probably true, but getting it in characteristic P would require, I mean, that would be more pain. That was more pain than I wanted to go through without an application. Characteristic 0, I think smoothness, I think the proof would go through okay, but characteristic P, I'd want to actually have an application before I went through the pain. Yeah.
Just the dimension. So it says that's a small
So I don't know how. I mean, I don't know how to make that. It's general. I mean, for the torus version, you could. I mean, the torus version, I think characteristic 0. I would be shocked if the smoothness wasn't. If you couldn't just change this proof a little bit. In characteristic P, though, I would worry much more.